Welcome to Biostatistics III Survival Analysis for Epidemiologists in R. My name is Mark Clement and I'm a lecturer in biostatistics at the Department of Medical Epidemiology and Biostatistics at Karolinska Institutet. The course website is biostat3.net. The course will run between the 9th and the 18th of November 2020, and the course catalog URL is shown at the bottom here. I'm the course director. The course administrator is Gunilla Nilsson-Roos, and the teachers include myself, Anna Johansson, Julia Leon-Tejeva, and Nurgul Bater-Bikova. As an overview of the course, we will cover these central concepts in survival analysis, including censoring, truncation, the survival function, and the hazard function. We will describe non-parametric methods for estimating the survival curves using the Kaplan-Meier curve and the actual method. We will show how to estimate rates and model those rates using Poisson regression. On day 3, we'll cover Cox's proportional hazards model and think carefully about the proportional hazards assumption. And then we'll also begin to explore some approaches for modeling non-proportional hazards. We'll show that there's a nice, close, and useful connection between Cox and Poisson regression. We will then introduce some parametric survival models, discuss risk sampling, particularly to do with nested case control studies, but also Cox. And then we will also discuss non-collapsibility of the hazard ratio. For the general format, what we'll do is the lectures will be recorded and made available. You can either go through those in your own time, or they'll be screened in the mornings, and then we'll be using the chat function. And then we'll also be doing exercises in the morning to review that material. In the afternoon, there will be computing labs via Zoom, and then TAs will be available. We do suggest some of the recommended exercises, but you're actually welcome to structure your own time so far as the labs. The course participants do tend to come from quite varying backgrounds, and that's actually a good opportunity for you to discuss some of your own analyses in the labs. We'll be trying to avoid Zoom fatigue, so I've tried to keep the late afternoons free. What feedback is welcome for ways to improve the format. What we found in the past is that a compulsory text doesn't work well because it's sort of hard to find the right level for the different course participants. We've provided extensive course notes and lab material. There are a number of books which are sort of more technical. The classical text is Breslow and Day, which is available freely online. For our core, has got access to the R book, which has got a useful chapter on survival analysis. We'll be using R in the lecture materials and the labs, and the download material is available from this URL. If you actually sort of go to biostat3.net and then R, you'll actually go straight to the exercises. The Biostat 3 package is available from CRAN, so once per course you should be able to just do an install packages from Biostat 3, of the Biostat 3 package. there may be some challenges with version 3 of R versus version 4 of R, because if you need to install the foreign package, that actually requires version 4. If you do run into this problem, ask us. The alternative approaches would be to install version 4 of R, or there are some workarounds, and I can help with that. Okay, key concepts. So, why is survival analysis a bit different to most other aspects of statistics? Is it's important to take into account the time dimension and the sort of the outcomes in survival analysis could possibly be reported as a survival proportion or as an event rate, and there are close mathematical relationships between those two measures. Most epidemiological cohort studies can and should be analysed in the framework of survival analysis. And importantly, time may be both a confounder and possibly an effect modifier. As we will discuss, there's a close relationship between Cox regression and Poisson regression. And what we want to do is have Biostat 3 build on top of Biostat 1 and 2, which means that we will sort of try to reinforce the view so far as adjustment for confounding and modeling for effect modification within a model framework. And you can do such things as reparameterize a statistical model to estimate different interaction effects. For this course, we've actually tended to use effect modification and interaction synonymously. However, some authors do define them quite distinctly, and there's, I think, that the reference 7 there is quite interesting. For the course plan, you can see the URL here. So after completing this course, you should be able to propose a suitable statistical model for addressing a specific research hypothesis using data from a cohort study or possibly a randomized controlled trial. You should be able to fit the model using standard software, evaluate the fit, and interpret the results. You should be able to explain the similarities and differences between Cox and Poisson regression. Importantly, you should understand the concept of timescales and how you can actually control for different timescales using statistical software, and you should be able to argue for which timescale is appropriate for a given research hypothesis. Not surprisingly, you should better understand the concept of confounding in studies and be able to control and adjust for confounding using statistical models. You should also be able to apply and interpret appropriate statistical models for studying effect modification and be able to use reparameterization to estimate appropriate contrasts. And you should be able to critically evaluate the methods for a scientific report for a cohort study. Okay, the take-home exam. The course grade is based solely on a take-home written exam. The contents of the exam will be similar to several of the previous take-home exams, although, and I should emphasize this, you will not need to write code for this exam. The exam requires that you understand the concepts of survival analysis and that you're able to interpret output from standard statistical software, specifically R. So the exam is individual based. Do not cooperate with anyone, although you are encouraged to consult the available and cite the available literature. The teachers will use Urkund to check for plagiarism. I'll release the exam around noon on Wednesday the 18th, and then the exam is due just over a week later. The exam will be graded and returned to you by the 4th of December. Students who do not pass the first exam will be offered a second exam within 2 months of the final day of the course. Do not write your answers by hand. Please use either Word or LaTeX or a similar format for your exam report. You should motivate all of your answers, and you should also show all calculations. That said, please write briefly but without loss of clarity. If you have to choose between brevity and clarity, I would go for clarity. You should define any notation that you use for equations, which is what you have to do for a publication anyway, and the exam report should be written in English. You are expected to interpret R computer code and output. Please email the examination report as a PDF to Ganilla. You should write your name in the email, but do not write your name in the document containing the answers, because I should be blinded to the respondent. Right, taking a bit of a breath here. I want to start off by defining some notation, and you won't need to come back to this slide as we work through the lectures. Hopefully not surprising to most of you is that exponential of x is the natural exponential of x, and then log of x is the natural logarithm of x. Sigma, the sum from I equals 1 to n of this expression here. So for this particular expression can be seen as being beta, so exponential of beta times x1 plus exponential of beta times x2 through to exponential of beta times xn. The pi, or the product symbol here, is the product from I equals 1 to n of 1 minus pi. So it's 1 minus p1 times 1 minus p2 through to the product of 1 minus pn. The integral symbol here is basically the area between the lower bound and the upper bound of this function. And the limit function here is, as the delta t gets smaller and smaller and closer to 0, the probability of having the event, assuming that this is the event time, between t and t plus delta t divided by delta t. And this is actually the probability density function. But this limit says make delta t smaller and smaller and smaller and recalculate this result. And as it gets closer and closer to 0, that this should approach a value. This will only be true if it is continuous. Useful also to review some of the properties of logs and exponentials. Don't forget that an exponential of a sum is equal to the product of the exponentials. The log of a product is equal to the sum of the logs, and that the log of an exponential is equal to the exponential times log of the base. So what we have is that the log is the inverse of an exponential, and that the exponential is the inverse of log. So it means these properties holds, and what we'll use a bit later is that if x is very close to 0, then 1 minus x is approximately equal to exponential of minus x, and we'll use this approximation a few times. To keep going with the formal definitions, what we do is we assume that t is a continuous random variable for the time to an event with time origin t0. Quite often we actually think of t0 as being 0 if we're thinking about study entry, but t0 could be defined in different ways. So then what we have is we have the probability density function with normally given a symbol f of t, which is the limit that we described before. So it's basically the probability of having the event between t and delta t just divided by delta t. Then we also have the cumulative distribution function, which is the probability that t happens up to and including little t, and the survival function is the probability that that the event time is greater than little t. So some of the mathematical properties here for the probability density function: it is non-negative, but it's also it varies between 0 and infinity. That the area under the probability density function is 1. So that means if you integrate from t naught to infinity of the PDF, then it should be 1. That's providing there's no cure, which is a special case. And that the probability of an event between t and t plus delta is approximately equal to the PDF times the change in time. Properties for the cumulative distribution function: it's interpreted as the property of having an event or a failure by time t. So because it's a probability, it's bounded between 0 and 1. At the time origin, it's 0. So f of t naught is equal to 0. And then as t gets increasingly large, then it goes this value goes to 1. And usefully, you can also interpret the area under the PDF between t naught and t. This value here is also equal to the CDF. Properties for a survival. Survival is equal to 1 minus the failure proportion. And it's interpreted as the probability of not having an event through to time t. It's also bounded between 0 and 1, and unsurprisingly, given that this is true, then we find that S of t naught is equal to 1, and as t gets larger and larger and larger, then this goes to 0. Again, this is assuming it's a proper distribution, and if you've got cure, this value might be greater than 0, and this value might be less than 1. So, and it's also you can also think about survival as being the area under the probability density function between t and infinity. So it's got this definition here. Okay, so that's a bunch of definitions. How's the time going? Good. So what we have is, for this particular example, we have a probability density function which happens to take this nice slow curve here. This shape can vary quite considerably. Don't forget that the area under this curve between t naught and infinity is 1. So then this is the cumulative distribution function. It starts off at 0 and is increasing and will get closer and closer to 1. And the survival function starts at 1 and is decreasing. What we find is that the area under the PDF here, this area here, is equal to the cumulative distribution function here, and then 1 minus that is equal to the survival function. This particular PDF is based on an exponential distribution which has a constant hazard, which we will define soon. Okay, survival analysis. In particular, we are interested in analyzing the time to the occurrence of an event. For example, the time until, the time from cancer diagnosis until when a cancer patient dies. Time to event analysis is also known as failure time analysis. lifetime data analysis, event history analysis, and survival analysis. Time to event analysis is used for cohort studies and for randomized controlled trials for outcomes with study participants followed from a well-defined, has to be well-defined entry time to an endpoint. So formal requirements for time to event data, 3 basic requirements. There should be precise, unambiguous definitions of the start and the end times. There should be an unambiguous origin for the measurement of time and for the scale of time. So that means what we're talking about here, we could be talking about time since diagnosis or attained age or a number of other different time scales. There should also be a precise definition of response or the occurrence of the event of interest. And we will discuss the concepts of timescale and how to choose an appropriate timescale later in the course. We can estimate a number of different parameters for time to event data. For instance, we could estimate the survival probability, which is the proportion who have not experienced the event at a given time point during follow-up. Could also estimate the median survival time, which is the time when half of the individuals would have had the event. We can look at event rates, the very close related hazard rates and incidence rates, which are describing the instantaneous risk that the event will occur at a given time point, conditional on survival to the time point. We could also do contrasts between some of these values and the most popular single number for contrasts in epidemiology has historically been the hazard ratios, which is the ratio of the event rates or the hazards between different groups, such as exposed versus unexposed, possibly adjusting for confounders. The focus for today's lecture is on how to estimate survival probability, and we'll in the later lectures we will cover these other measures. So it's probably useful for us to reflect on how survival analysis is different to other approaches. In some studies, the event of interest, such as death, is bound to occur if we are able to follow up each individual for a sufficient length of time. However, whether or not the event of interest is inevitable actually has no consequence for the design, analysis, or interpretation of the study. In some studies, the time to event is of primary interest, whereas in many epidemiological cohort studies, we are primarily interested in comparing the event rates between the exposed and the unexposed, particularly if we're interested in etiology. The basic statistical methods are similar for randomized and observational studies, although the observational studies may have a stronger need to control for potential confounding. That shouldn't be that surprising to the course participants. I think you've probably covered this in Biostat 1 and 2 and EP 1 as well. The characteristic that complicates the use of standard statistical methods is censoring. So you might have unobserved or interval values for the response measurement of interest. And censoring leads to differences in follow-up times between individuals. What we could do is we could think about the simplest ways that we could try and do analyses of time to event data. What we could do is we could have, say, 2 groups, and then we could have exposed and unexposed, and then those who have the outcome and those who don't. For that 2 by 2 table, if we have complete follow-up for everyone, then that's fine. you can use the 2 by 2 table, and that will give you a risk ratio. So if we'd followed 35 persons for 5 years and count how many died during 5 years, then we can correctly estimate the risk of dying within 5 years and compare that between two groups. The problem comes that if not all individuals are followed for the full 5 years, some may migrate out, some may migrate into the population, they could die, or they could be lost to follow-up. So then we have incomplete follow-up for some individuals. The deaths that we count during those 5 years will only be among those who are still being followed. Out of the 35 that we started with, we may miss some deaths since they are unobserved. So individuals may no longer be observed and still die during the 5 years. In that situation, we actually need to take the time at risk, or the follow-up time, into account in the analysis, and hence we need to use a survival analysis. So if you actually did have complete follow-up time, you can model risk using either logistic regression or log binomial regression, or you could use survival analysis. So right censoring refers to the situation where the individual can no longer be followed up and the events of interest has not occurred. In studying the survival of cancer patients, for example, patients may enter the study at the time of diagnosis, or possibly at the time of treatment in an RCT, and then they're followed up until the event of interest has occurred. Right censoring may occur in one of the following forms. You could have administrative or type 1 censoring, where there is a termination of the study before the event occurs. They could die to a cause that is not considered to be the event of interest if you're doing a course-specific survival analysis, and they could be lost to follow up, for example, if the patient emigrates. In these cases, we say that the survival time is right censored. With right censoring, we know that the event has not occurred during the follow-up time, but we are unable to follow the patient further. We only know that the true survival time of the patient is greater than the observed value. And if we do not account for the differences between the individuals by using survival analysis, then the results may be biased. As a graphical representation of censoring, if an individual has the event at 5 years, then we have the exact time, and that gives us the most information. If they're right censored at 5 years, it means that they haven't had the event, and it means that that this area under the curve, that we would expect that they will have the event somewhere between 5 years and infinity. Another form of censoring is left censoring, which is not that surprising. If it's left censored at 5 years, it means that they have the event somewhere between the entry time and that time. So it's somewhere in here, and that's actually the same as the cumulative density function. So, and if we've interval censored, it means that they have the event somewhere between a lower bound and an upper bound, which in this case is, and so this could actually be defined as being, I think it's f of 6 minus f of 4. So it's the area under this curve here. So we could have data that is exact, it could be right-censored, it could be left-censored, or interval-censored. So this is showing 31 of 35 individuals who have been sorted by their survival time in months. So if we can actually, so what we have is quite detailed data here. We've got sex of the, I think these are colon cancer patients, their sex, their age at diagnosis, stage at diagnosis. I think we can largely ignore that. This is the year of diagnosis and this is the month of diagnosis. This is the survival time in months. So there were this individual survived to 2 months and then they died due to another cause and they had this particular subsite. And then this shows this is survival time in months and this is the survival time in years. And then these are all sorted by their survival times. So this shows that you've got 1, 2 individuals who survived to 2 months. There's 3, 5, 7, 9, and you've got some other repeats here. So there's a small handful of ties. But if you're looking at the survival time in years, they're basically the set who dies in the first year, including that one. And then they're given a small value. Then these are the ones who die between 1 and 2 years. These are the ones who die between 2 and 3 years. So, and you've got a lot more ties here than here. So, status could be that they die due to another cause, that they die due to cancer, or that they are alive at study exit. So, in our initial analysis, what we'll do is we'll look at covariates for the year of diagnosis and their status time using survival time in months and survival time in years. Okay, so choice of outcome measures. In Biostatistics 1, we tend to consider modeling the mean and doing that using linear regression. And then for Biostatistics 2, we tend to consider modeling proportions, such as using logistic regression. The question here is, can we now apply those methods to time to event data? And the example that we'll take is for colon cancer. Let's assume that a new treatment was introduced in late 1992, and we are interested in studying survival differences between patients diagnosed at 1993 to 1994 compared to those diagnosed earlier. So what we do is we compare the proportion of patients who die between the 2 diagnosis periods with follow-up through to the end of 1995. So this means that patients who were diagnosed in 93 to 94 can only have follow-up for at most 36 months due to administrative right censoring. Whereas patients diagnosed 1985 to 1992 had follow-up for at most 11 years. Note that most patients do not have complete follow-up through to 11 years. So sort of what we do is we are going to use the Biostat 3 package, and we're going to use the dplyr for data manipulation. And then we, from the colon sample data, which is in the Biostat 3 package, we're going to mutate or transform it, and we're going to have a binary variable for those that were diagnosed from 1993, and then we're going to have a dead, which will be true if they're not alive, and false if they are alive. And then we can do a cross tabulation for the diagnosed from 93 and death from this new data frame. Then we can look at the cross tabulation, and then we can do a chi-square test. And what we find is that for the deaths, there was 1 in the second period and 18 for the earlier period. And then if we do a chi-square test, we get a p-value of 5%, but we also get this warning message here because the chi-squared approximation may be incorrect. And the reason for that is that the expected cell count for this value here is probably going to be less than 5. As the expected cell counts are less than 5 in the bottom row, we could instead use Fisher's exact test. This is Fisher's exact on the contingency table, and then we get a p-value of 3%. And this also gives us the confidence interval for the odds ratio. So for the exact data, looks like there's reasonably strong evidence that the proportion of deaths are significantly lower in the second period than in the first. That's not really that surprising. The proportion of deaths was lower among the patients diagnosed more recently, since those patients had a shorter follow-up time and they didn't have the same opportunity to die. So what we could do is we could also look at the average survival time or lengths of the lines between the two groups. So now we're talking about using the same data set. We're going to look at the survival time in months by the calendar period of diagnosis and do a t-test. And what we find is that in the second calendar period, on average, there were only 21 months, and in the first, there were 48, and that's a very strongly, significantly different results. So the patients diagnosed in the second period have a longer time. But again, that could be related to the length of follow-up available. So what we could do now is actually restrict to those who died. So then we could subset on those who died. But when we do that, we find in one group there's only one cell, and then we get this error saying not enough Y observations because of this cell here. What we would really prefer to have is some measure of risk of death adjusted for the fact that individuals were at risk for different lengths of time. And the methods used for making inference about proportions will only be appropriate if individuals all have the same time at risk, which is usually not the case for survival data. So what we would really like, so an appropriate, that is when we have a binary outcome and all individuals are at risk for the same length of time, then the proportion is an appropriate measure. And in this case, every individual contributes the same amount to the denominator. If, however, individuals are at risk for different lengths of time, then we use person time as the denominator and estimate the event rate. In this case, it's a mortality rate. So the event rate is the number of events divided by the person time at risk. So doing the calculation using dplyr, we use the dplyr library, and then we group this by the calendar period, and then we summarize these two groups for the number of events, so it's the sum of the deaths, and the person years, which is the sum of these survival months divided by 12. And then we calculate the rates using the events divided by the person years. And then we find out that the event rate is higher in the first calendar period than in the second calendar period. So to review, in survival analysis, the outcome has at least two dimensions: the event indicator and the time at risk. And the event rate is not the only appropriate outcome measure. It's also possible to estimate the proportion surviving or the proportion dying, while controlling for the fact that individuals are at risk for different lengths of time. And the survival proportions will be the focus for the rest of today's lecture. As some background to the datasets that we'll use through the course, there's a colon dataset, which is colon carcinoma 1975 to 1994, with follow-up through to the end of 95. A similar dataset for skin melanoma. There's the colon sample that we've already seen. There's also the diet data set, which is data from a pilot study evaluating food frequency over 7 days. And then the primary hypothesis is the relationship between dietary energy intake and incidence of coronary heart disease. And these data were analysed extensively by Cullen and Hills, which is a very nice textbook on epi methods. Before we start to describe the data sets, I thought I could give a very brief review of some of the sort of basic data types. What we have is that if you've got numerical values, which are double precision floating point types, 1.0 and -2 times 10 to the -5. What's interesting is that in R1 is actually assumed to be a numeric type, while 1L is assumed to be an integer. So we've also got characters, which are in quotes, and then factors. And then factors are actually categories with ordered levels, and we'll come back to factors when we're talking about design matrices. And then there's also dates. So you can actually do as date for the 1st of August 1969. The difference of dates is a diff time, which can be converted to a numeric using as numeric. Okay, so then if you do an STR on the colon dataset from the Biostat 3 package, then we find out that we've got over 15,500 observations with 16 variables. Sex has got 2 levels, male and female. Age is an integer. Stage is affected with 4 levels. The year of diagnosis is an integer. Survival time in months is numeric. Survival time in years is also numeric. Status is a factor, subsite, and then we've also got this calendar period, which is diagnosed 1975 to 1984 and diagnosed 1985 to 1994. Age group is a factor. Then we have these 2 dates, the date of diagnosis and the date of exit. We also have an individual identifier, which we'll use later. And then we also have year of diagnosis, which I think looks much the same as this. And then year of exit as well, which I think are derived from these 2 values. The melanoma dataset is very similar, except I think the subsite is defined differently. The diet dataset has got a quite different format. We've got a SEM-ID, got a CHD indicator, which is 0 and 1, and Y is the person time of exposure. High energy is derived from energy, and that contains two lactose. So it's a low energy diet and a high energy diet. So it's actually importantly, it's a factor. So job has got 3 drivers, conductors, and bank workers. The other things that are important here, I think we'll probably use the dates at some point and the years as well. So this is date of entry, date of exit, and date of birth. Year of entry, year of exit, and year of birth. So what we find is for the status variables for colon here, what we have is got 1 loss to follow up, 519 died due to other causes, a large proportion died due to colon cancer, and a moderate proportion was still alive at the end of follow-up. And it looks like there are more females than males. And then what we find is that the deaths here are less from melanoma, with more surviving. Right, so examples of events and right censoring. If the event is any cause of death, then examples are immigration and end of study. For a cause specific death, we also have then you could actually think about censoring due to other causes, and again, immigration and end of study. For breast cancer incidence, we have death, immigration, end of study, but then interestingly, we also have mastectomy. It's where if a woman has her breast tissue removed, then she's no longer at risk to get a breast cancer incidence. But what's important here is that the reason that she's had a mastectomy may be very closely related to her risk of going on to have a breast cancer, and that could be informative censoring. Right, survival function, importantly, it starts from 1, it's monotone decreasing. And the non-parametric estimator here, which I think is based on Kaplan-Meier, means that it's either you have steps, so you have like it's flat here and then a drop, and then steps and a drop. So what this shows is that there were very few individuals at risk, and it may well have been that there were only 5 or 6 at risk at this time point, so don't over-interpret these large jumps. We have time in months here, and the survival on this axis. And again, because you've only got the 35 patients, you can see that there's actually not a lot of information here. I think we've just covered most of that. The other thing is that we could have looked at the survival as a proportion. So to go back, what you could do is draw a line across here, and somewhere around here will be the median survival. So alternatively, what you could do is choose at 20 months, then you could actually go across and read off what the survival is. We will describe non-parametric methods for estimating the survival curves, and then you can talk about the interpolation is flat between the points, but we'll come back to that. So if you want to compare survival between males and females, what we find is that the males tend to have lower survival through here, and then you've got some overlap here and here. So well, what we can see is that the broad pattern is similar between the males and the females. It's possible that the males have got worse overall survival in this time in this broad area. Again, don't overinterpret the sharp changes here, because you're looking at very few being at risk, and these the two sample sizes here are small. So individuals in group 1 may experience slightly better or higher survival compared to individuals in group 2, but it's actually difficult to establish just from the plots. The rate of decline in the survival function is a measure of the risk of experiencing the event of interest, and in survival analysis it is called the hazard function, and we'll use the symbol lambda of t. Lambda. Patients in group 1 have better tend to have better survival for survival through to 850 days, but then have worse survival, although I would not overinterpret that. So, and this is possibly an example of non-proportional hazards, which we will come back to throughout the course. So we can express the survival experience of a cohort in terms of the survival proportion or the hazard rate. And in epidemiological cohort studies, where the incidence of a disease is the outcome rather than death, we often present the failure proportion, or 1 minus survival, rather than survival itself. We can model the hazard function or the incidence rate and estimate the hazard ratio or incidence rate ratios for comparing, say, exposed with unexposed. And oftentimes it may be that the hazard ratio rather than the survival function may be of primary interest. Right, back to some math. As we defined earlier, t is a continuous random variable for the time to an event with time origin t0. We've already defined that the probability density function and the solve function. Then the hazard, lowercase lambda t, is the limit as this delta t gets smaller and smaller for the probability of having the event between t and delta t, conditional, and this is the important part, it's conditional on survival to that time point. And then that risk per unit time, so that means that we divide through by delta t. And the cumulative hazard is, which you use a capital lambda t, is simply the area under the hazard function. So what we have is that lambda t varies between 0 and infinity, and it's the probability of an event between t and delta t, conditional on survival to t, if we multiply the hazard by the change in the time. As that gets smaller and smaller and smaller, that approximation gets better and better and better. For the cumulative hazard, it's non-negative, varies between 0 and infinity. It's 0 at the entry time and tends towards infinity for a proper distribution, and it's interpreted as the area under the hazard function. So mathematical relationships. Amazingly, survival can be calculated as the exponential of the minus cumulative hazard, and we'll come back and give a proof of this on Wednesday. So that means if you've got the hazard function, you can calculate survival, and if you've got survival, you can calculate the hazard function. This is shown here, that the hazard can be calculated from survival, as it's the slope for survival, the negative of that slope divided by the proportion surviving. So it's also, if you've got the cumulative hazard, you can calculate the hazard, and then this also shows that the minus log of survival is equal to the cumulative hazard, and so the rate of change of the minus log survival is also equal to the hazard. And finally, you can calculate that the hazard as the probability density function divided through by survival. So all of those quantities are very nicely related. Right, to calculate the survival function S of t, we've got the 35 colon cancer patients, of which we introduced in slide 25. And to estimate S of t, we could simply calculate the proportion of individuals still alive at selected values of t, such as completed years. So if we have 35 patients at the start, so that's the initial, and then 8 of the patients died during the first year of follow-up, then a fairly simple estimate for survival is 35 minus the deaths divided by the initial. So that's basically 1 minus 8 over 35. And then this shows 77% survival at 1 year. However, when we try and do the calculation for the second year, we have 10 patients who died, but 2 patients could not be followed up for the full 2 years. And this causes some challenges. So what we have, again, the first year, got 35, 8, no censored, and 1 minus 8 over 35. And then 35 minus 8 minus 0 gives us 27. We have 2 deaths. We have 10 total deaths, so 2 in the second year and 2 censored. And the big question is, how do we fill in the question mark? So what we could do is we could do 35 minus 2 as the denominator, and then 10 being the deaths. That would be one approach, but that will tend to underestimate the true survival proportion, since it ignores the fact that each of the 2 patients were at risk of death for between 1 and 2 years, but did not die while under observation. What we could do is ignore that and do your 35 minus 10. But then that will overestimate the true survival proportion, since we're assuming that each of these 2 patients survived for a full 2 years, which is not true. So 2 common and similar methods for estimating S of t in the presence of confounding are the Kaplan-Meier or product limit method and the actuarial or life table method. The cool thing about this is what we do is we can slice up time. In this case, we've sliced up in completed years. And then for each of the slices, we can calculate the probability of surviving that time slice, or that small time interval. So P1 is the probability of surviving the first year. P2 is the probability of surviving between 1 and 2 completed years. P3 is the third interval, P4 is the fourth, and so on. And then what we do is we calculate the probability of surviving at least 5 years from time 0 as the product of the conditional survival probabilities. So the probability of surviving from 0 to 5 is the product of this survival proportion times this survival proportion times this times this times this. And that's shown in this equation. The advantage of this approach is that we can appropriately account for censoring when estimating the probability of surviving a small time interval. And the same approach is employed by both the actuarial and the Kaplan-Meier methods. And we choose to estimate conditional probabilities for 1 year intervals in the example, but the intervals may be anywhere, so we can make the intervals wider or we can make them smaller and smaller and smaller. The main difference between the Kaplan-Meier and the actuarial methods is, well, there are two. There's one, how the default intervals are chosen, and two, the method for dealing with ties. Ties in survival data. If two individuals have the same survival time, we say that the survival times are tied. And many of the standard methods for survival analysis, such as the Kaplan-Meier method and Cox proportional heads model, assume that survival times are measured on a continuous scale and that ties are therefore rare. So some of the examples that we use in population-based survival analysis, ties are more common. So among the 9,000 people diagnosed with colon carcinoma, 490 died during the first month of follow-up, and 542 died during the second month. So, as a summary of the two estimators for non-parametric estimation of survival time, what we do is we split the follow-up time into time bands. If they're both deaths and censoring within an interval, then within the interval, Kaplan-Meier assumes that the events precede those censored. That is, everyone is considered to be at risk when the events occur. For the actuarial estimator, it assumes that half of the censored individuals are at risk. Then, for each of the intervals, we estimate conditional probabilities of surviving each interval. So the conditional survival for the interval is 1 minus the number of deaths divided by the number at risk for an interval, and then survival is the product of the PIs. The only difference between the Kaplan-Meier and the actuarial method, once we've specified the intervals, is the approach to dealing with the ties, and then that will affect the calculation of the number at risk and the conditional probabilities. You should note formally that the Kaplan-Meier approach is slightly biased in the presence of ties. So one should define time as accurately as possible to minimize the number of ties. If the survival times are generated on a truly discrete scale and ties are common, then the actuarial approach is preferred. What's quite nice actually is that the actual method can also be used with many small intervals. So what we have, going back to the data, we have 35 at risk initially with 8 deaths. So the PI is 1 minus 8 over 35. Then we have 27 at risk with 2 deaths. We assume that the censored are still at risk. So we have 1 minus 2 over 27. And then the product for survival is 1 minus 8 over 35. And then the product of 1 minus 2 over 27 times 1 minus 8 over 35. In contrast with the actuarial method, the data are just the same. The first value is just the same because there are no censored. But for the censored, that goes in here. and then we divide by 2. So then the only real change is the denominator here is 27 minus 1 compared with 27. And then this is using the same intervals. Kaplan-Meier, you would generally choose smaller intervals, and then as the number of intervals gets smaller and smaller, these two approaches become more and more similar. So it was published by Kaplan and Meier in 1958. It was published previously in German, and the Kaplan-Meier approach is essentially the life table approach, making the intervals as small as possible. So in practice, only the intervals containing an event can contribute to the estimates, so we can actually ignore all the other intervals. And to estimate survival, what we do is we first order the survival times in increasing time, and then we pull out the deaths or the events, and the notation here, we call them TI, where that's the first event or events, that's the second set of second event or events, and so forth. And then the number of deaths occurring at TI is called DI. If both censorings and deaths occur at the same time, then the censorings are assumed to occur immediately after the death times. And then if T is less than the first event, then survival is equal to 1. If otherwise, it's the product over all of the events that have happened prior to T of 1 minus DI over LI, where LI is the number of persons at risk. As we've already seen, a plot of the Kaplan-Meier estimate of the survival function takes the form of a step function, in which the survival probabilities decrease at each death time and a constant between adjacent death times. Censoring contribute in equation 1 by decreasing the number at risk. If the largest observed survival time, which we'll call Tmax, is a censored survival time, then the prediction of ST is undefined for T greater than Tmax. Well, if the last survival time is those dying, then S of T is assumed to be 0 from T being greater than Tmax. The survival time of the estimate can be obtained using Greenwood's method, and there is a reference for that. Right, so what we have here is this is now using the monthly data, which is the finest time step that we have available. We ordered the individuals by their times, and then once you've sorted them, then we can calculate that there were initially 35 at risk. In the first time interval, there were 0 deaths, and so what we have is that you've got for that interval, the conditional probability of survival is 1, and the product limit estimator is 1, and there's no standard error. And then what we have is for the second month, you still got 35 at risk. There were 2 events. That's 1 over 2 minus 35, and then the product of that value here and this value here gives this value here. and then from the Greenwood formula, we can calculate the standard error, and then we just change the number at risk, have the number of deaths, calculate the condition specific, do the product of that value and that value to get this value here. And then we just keep going all the way down. So we'll be using a number of different tools for survival analysis in R. The main function for doing survival analysis in R is called survival. That includes the serve fit for doing Kaplan-Meier, the serve split function for splitting time to event data. We'll also be using GLM for doing Poisson regression. We're using Cox pH in the survival function, sorry, in the survival package for doing Cox, and we'll be using Cox.zpH for testing for the proportional hazards assumption. There are a number of other utility functions here. One is that the life tab 2 is a function for doing actuarial survival using the serve function, which we will shortly introduce, and we'll do hazard smoothing using the mu_has_2 function. And then there's also a utility function here for tabulating event rates. These are all specific to the Biostat 3 package. And then we also have generalized survival models, also called flexible parametric survival models, which are available from several packages. One that we have written is RSTPM2, and the function is called STPM2. There's also a similar function called GSM, which has got much the same core interface. Right, part of model specification in both Stata and R and SAS as well is you need to be able to just define how the model is specified. And for time to event data, the survival package has popularized the choice of the serve function. And the serve function doesn't actually really change the data. What the serve function does is it helps to define what the data represent. So what we have here is we've got using the serve function for two event times, 10 and 15, and the 10 is an event and the 15 is censored. Now when we use this function, it returns these two values. This plus says that it's at 15 years it was censored. And then without having the plus here, that shows that that was actually an event. So this is for data representation. The serve function can also be used for left and interval censored data and left truncated data, which we'll come to shortly. So to calculate the Kaplan-Meier estimate of the cause-specific survival function by sex at 120 months, and to fit a Cox proportional hazards model with sex and counted period as a fix. First of all, for the Kaplan-Meier, we use the serve fit function with the serve to saying with the event times being survival time in months, and then the status is that that the event is dead due to cancer. And we want that to be given by sex from the colon data set. And then from that Kaplan-Meier, we want to get a summary of that for this object for the survival time at 120 months. Then for Cox, again, we're using the survival function, again for the same time and for the same outcome. And we want to adjust for, that's wrong, it should be just calendar period here from, again, the colon dataset. Then what we find is if we make a copy of the colon sample where we mutate or transform, where dead is equal to status is not equal to alive. So this is any cause of death. And then we save the object as being called fit from a serve fit, or that's Kaplan-Meier for survival time, for survival time in months, for any cause, for just for the whole group together from the sample, and then we do a summary, and then this gives us this very nice table where we have the time in months, the number at risk, the number of events, survival time, the standard errors from Greenwood, and then we can also get confidence intervals. Now the confidence intervals can be a little awkward because if you've got a very large standard error, you could have that if you go p plus 1.96 times the standard error, that could end up being greater than 1. And that would be a bit strange. What we do is we take the variance estimator from the Greenwood, and then we do a log. I think what do we do? Is it log minus log of p? We use that transformation. We do the confidence interval calculation on the transform scale, and then we back transform. And this is an example of the delta method. So what we do is we can then plot that Kaplan-Meier object, giving some nice X labels and some nice Y labels, and then we say that we actually want to turn off the confidence intervals. Otherwise, we would have had something that looks a bit like this. So, or even wider here. So, alternatively, what we can do is use a serve fit for the same outcome and times, but we want to stratify by stage from the full colon data set, and these curves are much smoother. And you see here that there's very fine detailed changes. And then we can plot that fit, again changing the labels, and then changing the line types and the colors. And then we're going to add a legend in the top right corner without having a box around it to have the same line types and colors for the levels for colon stage. And this is just a nice way to make sure that you get the labels in the right order. Again, we have survival on the y-axis and time in months on the x-axis. As we've already described, confidence intervals can be calculated for the survival proportions to actually be able to represent the uncertainty associated with the point estimate. And I think you know that already. I think you know that it's an interval estimate, while the estimated survival proportion is called the point estimate. So again, we could get a two-sided confidence interval by going p minus 1.96 times the standard error from Greenwood's method, and as a rule of thumb, the normal approximation, which is assumed here, is appropriate when both the number at risk times the risk of dying, and the number of risk times the risk of survival, the number of risk times the number dying are greater than or equal to 5. And then confidence intervals obtained in this way are symmetric about the point estimate, and can sometimes, unfortunately, sometimes contain implausible values. And then what we do is we sort of work on the log cumulative hazard scale and back transform. Great. So the life table method is also known as the actuarial method, and the approaches divide the period of observation into a series of time intervals, and then estimate the conditional survival proportion for each interval. And then the cumulative sort of function is again the product. So the only real change here is how the number at risk is calculated. So in the absence of censoring, it's just the number of patients alive at the start of the interval. However, in the presence of censoring, what we do is we do an adjustment for the censoring and assume that the individuals are censored halfway through. So what we do is the effective number of patients at risk is assumed to be the number initially minus half of the censored. So that means we now have L prime, which is the number at risk initially, minus half of the censored here. And then this formula here is otherwise just the same as the Kaplan-Meier. Now the assumption here is that the censoring is non-informative, and we're making the assumption that conditional on the values of any of the explanatory variables, that censoring is unrelated to prognosis. And I think this conditioning means that it's actually quite general. The problem, if censoring was informative, for example, if those censored were more likely to die, then we were going to be left with healthier patients in the study, which will show a bit better survival than the true survival of the patients. And for the exercises this afternoon, the first thing you'll do is you'll do the life table calculations by hand, which is sort of fun to do once because it's always sort of like getting the rows right and getting the cells right is sometimes tricky. So again, for the Kaplan-Meier, we have 35 initially at risk, then we have 8 censored, so this is just 1 minus 8 over 35, and then here, this PI here is 1 minus 2 divided by, it's 27 minus 2 over 2. So it's 1 minus 2 over 27 minus 2 over 2. And then for this one here, you've got 23 at risk, 5 deaths, 4 censored. So it's 1 minus 5 deaths minus 23 initially at risk, adjusting for half of the censored. So, and then these are all just the products of these values here. And that's why when you don't have any events, these don't change. Another useful measure of survival is the median survival time. It's the time at which survival is equal to a half, and then the median survival time on the next slide is approximately 1.3 years, and then the median can be estimated by extrapolation, provided the survival function. The median can, if it doesn't sink below 0.5. So if you had a curve that does this, and then this is half, you could possibly do an extrapolation from here down to say when that would happen. So what we have is that the observed data do drop below 0.5. We go across and then down and then solve here, and then we can also get a confidence interval for that estimate. Okay, various tests are available for testing the equality of solver curves, and the most well-known of these is the log rank test. However, these tests are actually rarely used in observational epi, as we prefer to use modeling, because the models mean that we get an estimate of the size of the effect, because the log rank just gives us a p-value, and it also provides greater possibilities for confounded control and effect modification. What's interesting is that the log rank test assumes proportional hazards. So if we have two groups and when we do a Cox model with one explanatory variable, we essentially get the same p-value from the log rank test as we do from the Cox. But then we also get the hazard ratio and confidence interval from the Cox. So it actually gives us more information, and we can also control for potential confounding variables. One of the challenges, so what we could do is we could basically say, let's estimate survival at 2 years, and then just compare that between two groups. But if you actually do fix the time interval, that actually wastes some of the available information. Okay, to compare survival at a fixed time point, we could simply sort of choose 5 years and sort of say, is the survival different in one group at 5 years compared with another group? But that actually wastes all of the rest of the times, so far as survival could be higher or lower earlier than that, and it could be higher or lower after that. So what we do instead is look for methods which actually take into account the differences across the observed solver curves, and then compare for equality of those curves. And the most common test is the log rank test, which is non-parametric. What we do is we start by tabulating the number at risk in each group and the total number of events or deaths at each time point when one or more deaths occur. And then under the null hypothesis, the two solver curves are the same, and under that null hypothesis, the expected number of deaths in each group will be proportional to the number at risk in each group. Okay, that's the assumption. So at 2 months, we observed 2 deaths. One was male and one was female. And then conditional on 2 deaths being observed, we would expect 2 times of for the 19 males, we expect of the 35. So those 2 deaths would be divided up with 1.086 deaths for the males and 2 minus 616 over 35 for the females. And then all we do is we keep on doing that for each of the event times, and then we calculate the totals of the observed and expecteds for each group. So the actual total number of observed males and observed females, expected males and expected females. And then we get this classic chi-squared test, where you've got the observed minus the expected squareds divided by the expecteds for the first group, and the observed minus the expected squareds divided by the expecteds for the females. Under the null hypothesis, this value will follow approximately a chi-squared distribution with 1 degree of freedom. So then if this is greater than 3.84, then we can reject the null hypothesis and conclude that there is a statistically significant difference between the two survival curves. So what we do is you've got 2 times 19 divided by 19 plus 16 to give that expected, and then 2 times 16 divided by the sum of that and that to get the expected here. And then for the 3 here, we have 3 times 18 times the sum of those two to give that, and then observed deaths. Oops, it's not 3. That's the time. Here, 1 and 1, 1 and 1. So there's 1 death. So that's 1 times 18 divided by 18 plus 15 gives that value there. And then 1 plus 15 divided by 15 plus 18 gives that value there. So these are the observed, and then these are the expected values here. Then we sum up the observeds, and that gives us O1. Sum up the expecteds, and that's E1. Sum up the observeds. Sum up those, it comes to 11. Sum up those, comes to 8. Expecteds, 10. Expecteds, 8.5. What's interesting is that this is very slightly, the expecteds is very slightly lower than the observed, and the expecteds is very slightly higher than the observes. Then we plug this in, and we get this value of 0.056, which is less than the cut point of 3.4, which implies that there's not significant evidence for a difference in survival between the males and the females. And for this data set, that's not so surprising because the numbers are quite small. So then for K groups, you just expand this, where you actually sum the observed and expecteds across the K groups, and you get a chi-squared with K minus 1 degrees of freedom. So the log rank test is designed to detect departure from the null hypothesis, in which the two hazards are assumed to be proportional over time, but it is insensitive to the situation when the hazard functions cross. So, and in particular, the log rank test puts equal weight on every failure, really irrespective of the number of risk at the time of failure. So it's equal weight on the failures. So an alternative approach is the generalized Wilcoxon test, which is constructed by weighting the contribution of each failure time by the total number of individuals at risk. And in that sense, it's actually more sensitive to the differences early in the follow-up period. And it's more powerful than the log rank test if the proportional hazard assumption does not hold. It's difficult to apply the log rank test while simultaneously applying for potential confounding variables, and then we would prefer a regression approach. For a randomized controlled trial, however, potential confounders may be controlled for in the randomization, and so then we could simply just use the long-run test to compare survival curves for the different treatment groups. And I think actually that's the main place that I've seen the log-rank test used consistently is actually in the RCT setting. So, but it doesn't provide more than a test of significance. So it doesn't actually tell us about the size of the difference. And you have to actually interpret the test statistic to see even what the direction is. So while if you use a regression approach, it allows us to determine both statistical significance and to estimate the size of the effect. Straightforward to do NR, and the survival package provides the serve diff function. So we specify the survival time using the serve function. So it's survival time in months for all cause mortality stratified by sex. So we were basically this is say, can you show us the differences in the survival curves by sex from the colon sample? What we find is we have 19 initially at risk in the males and 16 initially at risk. We observe 11 and 8 deaths. We get the expected, which has been 8.49 and 8.51. These are the components. I think that these are used for the variance calculation. And then what we find is that's the chi-squared statistic, which gives us a p-value here, which shows very no evidence whatsoever for a difference in survival between males and females. Don't forget the null hypothesis here is predicated on the model being correctly specified, and it does assume that there's no uncontrolled confounding. Irrespectively, the numbers here are very, very small. So even if there was remarkable confounding, we probably wouldn't have the numbers to adjust for that. To do the same analysis using Cox, we can use the Cox pH command from the survival package for survival time expressed in survival time in months for all cause mortality, adjusting for sex from the colon sample. And this shows here that's the log hazard ratio, that is the hazard ratio, and that's the confidence interval for the coefficient. And then this is a test. And this gives us a WOLD test for this coefficient because we've only got the 1 degree of freedom. The likelihood ratio test is very closely related to the WOLD test. So, and it shows that we started off with 35 at risk, and there were 19 events. I think the main point here is that the standard error is very large because I think the number of events is quite small. Okay, to summarize what we've covered today, that we need to do time to event analysis if we are interested in studying the time to an event, and that individuals in a study may be followed for different lengths of time and therefore may be at risk for different amounts of time, and that censoring is the main driver for using specialized methods. So we need both an event indicator and one or more time dimensions. And the outcomes can be expressed either as survival proportions or as event rates or closely related hazards, and that comparisons between groups are primarily made using hazard ratios. We've described several approaches for estimating the survival function, and we've described that you can use the log-rank test or the generalized Wilcoxon test for comparing differences. For observational epidemiology, we would generally prefer modeling. I think what you find is that the Kaplan-Meier curves provide for a very nice description of the data, but they are potentially confounded. And the modeling means that we can do some better adjustment for confounding. There are ways to do adjusted log rank tests, but actually we would generally prefer the regression context. The nice thing about doing the modeling is that it actually provides a stronger focus on estimation rather than testing. It also means that we can study effect modification, and it's extendable in a number of other useful ways. For this afternoon, there are the recommended exercises include doing a hand calculation of Kaplan-Meier, and then doing the same calculation using R, then doing an analysis using the melanoma dataset, particularly looking at survival proportions and mortality rates. And then also looking at cause-specific survival for the third exercise, first doing this graphically and then using the log rank test, and then finally comparing various approaches to estimating the 10-year survival proportion. You are welcome to do those exercises in whatever order you feel like. We include here a number of references, including the one by Tyler van der Wiel, which is looking at the distinction between interaction and effect modification. And what we'll do is meet on Zoom at 1 o'clock. Thank you for your attention.